Hi everyone, in this video I'm going to show you how we compute the confidence interval for the difference in population means under the two-sample t-test and how we interpret that confidence interval. Now, the confidence interval is constructed differently when you're testing a non-directional versus a directional hypothesis. So I'm going to start with a non-directional hypothesis context. So for example, the non-directional hypothesis is stated that the difference in the means, population means, is equal to 0. And so when you reject this null, which we did in the previous video using p-value, what we've learned is that the difference between the population means is not equal to 0. That's our conclusion. What we haven't learned are what are reasonable values for this difference. And that's where the confidence interval comes into play. So what we're going to do is calculate a confidence interval with a certain percent confidence. And it's going to be for the parameter under the null, which is the difference in population means. Now, the size of the confidence interval depends on your alpha level. So for instance, if you're going to be using an alpha level 0.05, you're going to be computing a 95% confidence interval. So I'm going to demonstrate now how we compute this confidence interval when we're testing a non-directional hypothesis as shown here. And so the interval, as I said, is for the difference in population means. We're going to have a lower limit and an upper limit. First, we'll put in our statistic of interest, which is estimating the parameter, which is the difference in sample means. Then we're going to add a margin of error. The margin of error is being measured by a t-value from the t-distribution with the degrees of freedom n-2 associated with the alpha divided by 2 percentile. So for instance, as alpha is 0.05, we're looking for the t-value at the 2.5th percentile in the t-distribution. Then we'll multiply that by the standard error of our statistic, the difference in the sample means. The upper limit is very similar. Again, we start with our statistic, the difference in the sample means, and we're going to add some margin of error. But in this case, instead of at the alpha divided by 2 percentile, we're going to do 1 minus alpha divided by 2. So this, for an alpha level of 0.05, would be the 97.5th percentile. And we again multiply that by the standard error, the same standard error. So as an example, we'll plug in the numbers here. So the mean for the two groups, for group 1 is 25.38, minus the mean for group 2 is 34.63. This is an estimate for the difference in the population means using the sample. The t associated with the 2.5th percentile, and you can get that from Excel or using R, is negative 2.14. And the standard error, which we computed when computing the t statistic, is 3.31. The upper limit is very similar. We have 25.38 minus 34.63. Again, that's the estimate. And then the t associated with 97.5th percentile, because the t-distribution is symmetric, is a positive 2.14. And the standard error, again, is 3.31. And so the lower limit becomes negative 16.32. And the upper limit is a negative 2.16. So one way I like to think about this interval is that these are reasonable guesses for what the difference in the population means could equal. In fact, if you put these values under the null, instead of 0, any one of these values, you would not reject the null hypothesis. So there are three things I like to consider when I'm interpreting a confidence interval when testing a non-directional hypothesis. The first thing I have to consider, and the question I ask myself, is 0, or the value under the null we're testing, in the confidence interval? If the answer is no, so if no is not in there, then we reject the null. And so you can see here, we can use the confidence interval to test this null hypothesis, in that the value under the null, if it's not an interval, we're rejecting no because we're saying that's not a reasonable guess. If the answer is yes, then we do not reject a null. And so this part here is analogous to the p-value in the sense that it's telling us to reject or not, and it has to do with statistical significance, just like a p-value is used when we compare it to an alpha level. The second question I ask myself, is the confidence interval far from 0? Now I'm using 0 because that's a value under the null. And so this has to do with what's called practical significance. In other words, you can have a statistically significant result where 0 is not in the interval, but the interval is very close to 0, indicating that they're practically the same. And so practical significance is a very important part of the analysis to judge whether we have a meaningful difference. And the third, and by the way, this practical significance, for you to make a judgment about practical significance, you truly need to understand the scales of your variables to know what is a meaningful difference. The third question I ask myself is, how wide is the interval? So how wide is the confidence interval? This has to do with how informative our data are in telling us where the difference in population means. So essentially, it's how informative our data are, essentially. The wider the interval, the less informative our data. And the way we reduce the interval to make it narrower is to increase the sample size, which decreases the standard error, and it also impacts these t-statistics because when you have a larger sample size, you have more degrees of freedom, and the t-distribution gets more narrow. Well, that's how you calculate the confidence interval when testing a non-directional hypothesis. Well, what if we're testing a directional? Well, I look at the alternative hypothesis when testing the directional. And so, for example, if I put less than 0 here, when we calculate our t-statistic and convert it to a p-value, we did a lower tail test. Well, when you're doing a confidence interval and you have the less than sign here, you calculate only the upper bound of the interval. So it's no longer an interval, it's actually just a bound because the other side goes to infinity. As an example, again, here's our parameter. We're only going to calculate this upper limit. And that's because we have a less than sign here. If we had a greater than sign, we only calculate the lower limit. And so it's still the same, it's similar. We have our statistic. We're going to add some amount of error. But now here, because we're calculating just the upper limit, we're going to be looking at the upper part of the t-distribution. Instead of t minus alpha divided by 2, we're going to do t minus alpha. So we're going to be looking for example, the t associated with the 95th percentile from the t-distribution with 14 degrees of freedom. And then we multiply that by the standard error of the difference in our statistic. And so, if we plug in the numbers, the difference in the means are the same. It's 25.38 minus 34.63. Our t now, instead of 2.14, is actually 1.79. It's smaller because it's going to be closer to 0 given the fact we're looking at the 95th percentile. The standard error is the same, 3.31. So now our upper limit is negative 3.42. And if you compare that to the previous upper limit, that was negative 2.16, you can see this value is further from 0. When I interpret this interval, I use the first two questions. Is 0 in this interval? You can see it's not. We're saying that the difference between these parameters, our best guess is negative 3.42 or less, where 0 is not in there. So I reject a null, so I can still use that question. The second question I ask myself is, how far is this interval from 0? Again, that has to do with practical significance. The third question, how wide the interval, is less informative. In fact, it's not informative here because this side over here is actually negative infinity. And so that's obviously a huge interval. So we're not looking at the width of the interval in that situation.